Hello, I am Dr. Cam Ng. I am the Associate Professor at the Department of Civil and Architecture Engineering and Construction Management within the College of Engineering and Physical Sciences at UST of Wyoming. My research areas are transportation geotechnics, energy geotechnics, and innovative construction management. I am currently leading several research projects relating to energy geotechnics funded by School of Energy Resources and Department of Energy. My research focuses on experimental rock mechanics that relies on expensive and advanced equipments for experimental studies. High pressure and high temperature track seal equipment for rocks is rarely available for research due to high purchase and maintenance costs. In addition, many current track seal rock equipment in use could not fully simulate subsurface conditions and meet the current research demands, such as the carbon sequestration research. To acquire the most advanced research equipment for rocks and other materials, National Science Foundation, through the MRI program, funded the project to acquire the high temperature and high pressure true track seal equipment with multi-phase flow system. Here in the room B125 of the engineering building at the UST of Wyoming, part of my multi-user geotechnical and geomechanics research laboratory. This is the high pressure and high temperature true triaxial equipment with a multi-phase flow fluid flow system known as the AutoLab 3000, manufactured by New England Research. The AutoLab 3000 can be applied to civil infrastructure, water resources, environment, energy, geosciences for research in rock mechanics, material science, geophysics, hydrologic science, thermohydraulic, mechanical, chemical processes. This system will improve the reliability of our civil infrastructure, reduce risk and economic losses during subsurface exploration, ensure a safe and permanent storage of pollutant, and improve extraction of drinking water, hydrocarbons, and alternate energy sources. Currently at UST of Wyoming, our research team is investigating the fundamental thermo-hydro-mechanical, chemical, biological processes of materials that we need the true traction machine like this to help simulate the in-situ subsurface conditions or extreme conditions that are unattainable through a conventional traxial equipment. This equipment helps advance the basic knowledge on the thermo-hydro-mechanical, chemical, biological interactions and multi-phase flow behaviors of porous media that benefit the energy industry in Wyoming, which faces a challenge in the current energy transition. The equipment can apply three independent principal stresses, heat multiple pore fluids at the same temperature of the test specimen, perform coupled process measurements over complex loading trajectories and multiple phase flow conditions to reveal the physics behind complex failure mechanics of the material. The AutoLab 3000 provides the integrated measurements, analysis, and reporting of elastic velocity, permeability, resistivity, pore volume, compressibility, and deformation of a test specimen fluid pore and confined pressures to 200 megapascal or 20 ksi. The system has a maximum axial loading of 3,560 kilonewton or 800 kips, capable of testing most rock and hard materials with diameters from 25 mm to 100 mm or 1 inch to 4 inches. One of the unique features of this equipment is the capability of heating multiple pore fluids entering the pressure vessel at the same temperature as the specimen. This feature is important for geomechanics research since subsurface fluids share the same temperatures as rock, and fluid temperatures have tremendous effects on rock stress strain behaviors, pore compressibility, permeability, rock fluid chemical reaction, and fluid transport. Furthermore, the equipment has the capacity to simulate high pore fluid and confined pressures and temperatures that exceed most typical deep reservoir conditions. The entire triaxial vessel and the pore pressure intensifiers of this equipment are housed in a furnace capable of heating the system to 150 degrees C or 300 Fahrenheit. This configuration ensures that the pore fluids entering the pressure vessels are the same temperatures as the specimen for equal heating. This equipment is retrofitted with one confinement pressure intensifier and three corrosive resistant pore pressure intensifiers constructed with titanium or C276 pestalloy that are compatible with water, brine, and gas, including CO2, for fluid substitution and continuous flow experiments. This allows for the complexity of the geometry and the physics in porous media deformation induced by fluid transport to be investigated to advance the understanding of thermo-hydro-mechanical chemical interactions. The equipment can perform a couple process measurements over complex loading trajectories with minimum user interventions. This system is supported by an AutoLab software that controls the loading path and temperature profile during each test, stores the data, and processes the results at the conclusion of the experiments. These couple measurements provide comprehensive data to facilitate the understanding of the time-dependent relationship between physical and mechanical properties, which could not be accomplished with most triaxial equipment.